This section describes the boot MIPS code and walks you through the booting of a coherent processing system. The boot MIPS code was designed to boot any MIPS core. It is arranged so that you can compile the code to only use a subset that is needed for a particular core. We are going to look at the code needed for a coherent processing system, or CPS. It is intended to aid you in becoming familiar with initialization of the MIPS coherent processing system. Some of this code should look familiar to you. It is similar to the ones shown in programming a MIPS core class, so some of the steps I will go through quickly. Here is a diagram of a coherent processing core that the boot MIPS code will initialize. A coherent processing core is made up of 1 to 4 single cores with an L2 cache, debug control logic, and optional inter-thread communications unit. A coherency manager, or CM, is the cache coherence domain control logic. A global interrupt controller, or GIC, is the system interrupt control logic. The cluster power controller, or CPC, is the power domain control logic. The memory map configuration registers configure and control the global interrupt controller, coherency manager, and cluster power controller. And the I/O coherency unit, or IOCU, controls the data coherency between external devices and the L1 and L2 caches through the coherency manager. This class section will step you through the boot MIPS example code. See the boot MIPS example boot code for MIPS cores application note on our website for more information on how to get and install this code. In the code, some of the general purpose registers are assigned specific values. These registers have been assigned to aliases using #defines so that the code will be more readable. Note that this does not follow the ABI while the boot code is executing, which should be fine since we don't call C functions until the very end of the code. We don't expect this code to cause any problems, but just in case, the exception vectors are programmed to cause a debug exception using the SDBBP instruction. If you are using a multiboard, the target resident debug exception handler will update the multi-display with the value in the CP0 DEPC register to aid in the debugging of an unexpected exception. If you have an EJTAG probe attached, control will be given to the probe, which will then be in control of the CPU that took the exception. I will use the following terminology in this course. A VPE stands for Virtual Processing Element. This is used in reference to a core that implements the multi-threaded ASE. Each VPE has the functionality necessary to support threads executing privileged code such as boot code, exception handlers, interrupts, and the execution of an OS. In the context of this course, a VPE is synonymous with a processor unless otherwise called out. The term core refers to each core in the CPS. A core can be made up of 1 or more VPEs in a multi-threaded system. A TC stands for thread context. This is used in reference to a core that implements the multi-threaded ASE. Each TC has the functionality necessary to support a thread of execution. All of the processors will execute the boot code in the start.s assembly file. The file is divided up into sections. The execution of each section will depend on which processor is executing the code. Here is a flowchart of the boot code. The init common resource section is executed by all processors in the system. This code initializes resources that are specific to each processor. These resources include the GPRs, processor-specific CP0 registers like the status, count, watch, and cause, and the TLB and the GIC. The init core resource section is executed only once for each core in the CPS. So on an MT system, this means that only VPE0 of each core will execute this code. It initializes the L2 caches at this point for core 0 if they cannot be disabled. This is because on some of the early 1004Ks, they could not disable the L2 caches. The later releases of the 1004K and all interactive cores can disable the L2 caches and will skip this step until the L1 caches have been initialized and the code can be run out of cache. This will make execution much faster. This section then initializes L1 caches and the inter-thread communications unit. The init sys resources section is executed only by core 0. This section initializes the coherent processing elements such as the cluster power controller, coherency manager, memory controller, and L2 caches. It also copies the C code to RAM and clears the BSS section. Once this section has been completed, all processors in the system are released from reset and can begin their boot process by using this same code. Each core then joins the coherent domain, and for empty cores sets up the second VPE so that the VPE can execute this boot code. The init section is executed by all processors. It sets the exception return address to the address of the main C function and then calls the ERET instruction, which ends the boot process and will start executing the main function. This slide and the ones that follow will walk you through the execution of the code in the start.s file. The call from the start.s file will be shown, and then I'll walk you through the function that is called. To start, you see the init common resources label and the first call to the init GPR function. The init GPR function is in common/init GPR.s file. To resolve the address of the function, the code loads the address of the init GPR label into the register and uses the jump and link register instruction to jump to the address and place the address of the instruction following the no-op into the return address register, register 31. The init GPR assembler function does as the name suggests and initializes the general purpose register sets. It first sets all registers in each register set to the hex value of dead beef. This can be helpful when debugging the boot code, because if you are reading a register that has the unlikely value of dead beef, you haven't set that register in your code and probably should not be reading it. The code also loops through all shadow register sets, if any, and initializes them. Shadow register sets will only exist for non-multi-threaded processors. Multi-threaded processors, such as the 34K, 1004K, and Interactive, do not have shadow register sets. Instead, they can designate the register set of a TC to be used as a shadow set. Each TC will go through this code and initialize its own registers later. Next in start.s is the call to set GPR boot values. This code is located in the setGPRBootValues.s file. The code in that file varies from core to core, so it is not part of the common code. The code sets up some of the aliased registers. These registers are defined with the #define statements in the common/boot.h file. The first part of each alias name is the actual register number, so when you're debugging this code, it should be easy to follow which actual registers are set. The first is the R1 all ones register. This sets up GPR1 to all ones. It'll be used many times in the code in conjunction with the insert instruction. It simplifies the code because we can use it over and over again without having to set up a register each time it is used with the insert instruction. Next, the code reads the eBase register CP0 register 15 select 1. The eBase value is used to set the CPU number in GPR23. The CPU number is stored in bits 0 through 9 of the eBase register. In the case of MIPS cores, we only need the first 4 bits to determine the CPU number, since that covers the maximum number of CPUs in our multi-core designs. The core uses the extract instruction to extract 4 bits starting at bit 0. Note, the CPU number being extracted is set using the hardware interface SI CPU num pins. For an MT core, there is a different CPU number for each VPE. To get some feedback during the boot process, it's helpful to have some kind of visual display. On our Malta evaluation board, there is an alphanumeric display, and the code sets GPR24 to the address of that display. Characters written to this address will be seen on the display. Of course, you will need to change this for your system. The global pointer is common to all processing elements. Its address is defined in the linker file and set by the linker. This address will be used to reference shared global variables. The MIPS API designates that register 28 be used to hold the global pointer addresses, so the code sets it here. Part of each processing element's context is its own stack. The stack is used to hold the local variables while executing a function. It also holds other contexts such as GPR values that are saved to the stack when a function is called and then restored when returning from the function call. In this case, the constant called stack base adder has been set by the programmer to a point in memory designated for use for the processor stacks. The MIPS API designates that register 29 be used to hold the stack pointer. The code first writes the stack base adder to GPR29, then manipulates it using the CPU number so each processing element will have its own stack. The boot MIPS code can be used for either a multiprocessor system made up of multi-threaded cores or only single-threaded cores. An MT core has the MT bit set in config 3. But you just can't read config 3 register to see if the MT bit is set, because on non-MT processors there will be no config 3 register, and the operation of trying to read the config 3 register will have undetermined results. In other words, nothing good will happen. To read the config 3 properly, the code first needs to read the config run register and make sure that the M bit is set. The M bit in the config 1 register indicates whether or not it has a config 2 register. The M bit is bit 31 in the config 1 register. If this register is treated as a signed integer, the bit will be the signed bit, and if the bit is set, the register would appear as a negative value, or a number less than 0. The simplest way to test the bit is to see if the register is greater than 0, using a branch greater than 0 instruction. The code then looks at config 2 register in the same manner as it did config 1. The code reads the config 3 register, isolates the MT bit, bit 2, tests it, and branches to the no MTSE function if it's not set. If the code has determined that it is executing on an MT processor, it will set GPR10 to 1. It will use this register in cases where it needs to do a special configuration for MT. The rest of the code will save MT-specific data in specific registers. It will read the CP0 TC bind register and save the number of the VPE context it is executing in right now into GPR9, and it will save the TC it is executing in to GPR18. Next, it will read the CP0 MVP comp0 register to set the GPR21 to the number of TCs within the core and set GPR20 to the number of VPE contexts in the core. Then the core will branch to check to see if it is a coherent processing system. Now the code needs to determine if it is running on a multi-core system. It does this by reading the CP0 processor ID register into GPR25. The code extracts the core ID and implementation bits. Then it compares them with the values for the specific core it was compiled for. In this case, it was compiled for an interactive core. If the test passes, it branches to setting up the Coherency Manager registers. If it doesn't, it exits to the debugger. If the code determines that it is executing on a coherent processor, it sets GPR11 to 1 to indicate that we have a coherent processor. R11 is CPS, will be used in several places in the code to branch to the appropriate execution path. The coherent processing system contains a structure that determines the configuration of the system. This structure is called the global control block. This structure contains registers that can be read to determine the configuration elements within the CPS. These registers are called the Global Control Registers, or GCRs. Many of the registers can also be written changing the CPS configuration. To verify that we have a correct global control block address, the code will compare a given address of the control block with the one that is stored within the block itself, located in the GCR base register. The given address is set by a #define. Consult your SOC designer to determine the value of this define. If the given address is not the same as the address in the GCR base register, something is wrong, and this system should not be treated as a coherent system. The value in the GCR base address is a physical address, so before the code compares the given value, it needs to convert it to a physical address. That's done by simply clearing the top 3 bits by using the insert instruction and GPR0. This line of code takes the first 3 bits of GPR0, which is always 0, and inserts them starting at bit 29 into the GPR register A1. Then it loads the GCR base register that is located at byte offset 8 into A0. The starting address of the GCRs is located in the memory map on a 32-byte boundary, so the lower 15 bits of the address will always be 0. The GCR base register uses the lower bits to store additional information. Therefore, to get the correct physical address, the code needs to clear these bits that are now stored in GPR A0. The code checks to make sure the 2 GPRs are equal and branches to the GCR found function if they are, or issues a debug breakpoint instruction to stop execution. Now that the code has determined it has valid GCRs, it will save the address in GPR22. The code stores the GCR CLID into GPR8. The GCR CLID is the number of the core that is executing this code within the coherent processing system. The GCR CLID is located within the core local control block. The core local control block is at offset 2000 hex from the GCR base address, and the GCR CLID is located at 28 hex within the block. Putting those together, you get 2028 hex offset from the GCR base. Now the code will save the total number of interactive cores in the system. This information is stored in the GCR config register located at offset 0 from the GCR base. Bits 0 through 7 contain the value, so these bits are extracted from the register value and stored in GPR19. Now we are done with the init GPR function and the code returns. Back to start.s. If the code is executing on core 0 VPE 0, then it clears the display on the multiboard. The code calls the init CP0 function. The init CP0 function is much the same as it is for a single core, so I won't cover it in detail. The first thing it does is set the status register to a known value for this board. Next, the code checks for watch registers. If the WR bit 3 in the CP0 config 1 register is set to 1, then the core has at least one watch register. Set the GCR v1 to the initialized value for the watch registers. This will clear watch conditions. Use GCR v1 to clear all watch conditions. Read the watch register high and check to see if the M bit is set, bit 31. This is set to indicate that there are at least another watch register. And branch to done if it is not set. In the branch delay slot, clear the watch low register. Continue until there are no more watch registers. Next, clear the CP0 cause register to avoid spurious interrupts once interrupts are enabled. Clear the CP0 compare register to clear timer interrupts. Then the code returns to start.s. Back in start.s, the code reads the config register and checks the TLB MMU field by extracting it to V1 and sees if it is set to 1. If it is not, the core does not have a TLB, so the code will go to the end of the function. Next, the code checks the VPE number that is executing the code, and if it's VPE 0, it branches to do TLB, because if there is a TLB, VPE 0 will always have a TLB to initialize. Next, the code will only execute if it is executing on VPE 1. The code checks to see if the TLB is shared. If it is, it will skip the init TLB call. If it is not, then it means that VPE 1 has its own TLB and needs to be initialized, so it will fall through and call init TLB. The highest TLB entry is stored in V1. This will be used as the first index into the TLB. Now clear all the entry registers, so we will initialize the TLB entry fields to 0. To do this, we use the same move to coprocessor 0 instruction using the general purpose register 0, which always contains a 0, and move to the corresponding coprocessor 0 register. Load A0 with the address to be placed in the entry. Note, it will not be valid, but it will ensure that the TLB does not have duplicate entries. Now we will use a loop to initialize each TLB entry. The next TLB entry pair label in the left column is the label of the start of the loop and the point we will loop back to. Remember, we stored the highest number TLB entry into V1. We will use it here to decrement through the TLB entries from the highest to the lowest and to program the TLB index entry. The code uses the move to coprocessor 0 instruction to copy the contents of V1 into coprocessor 0 register, which is the index register. The index is the TLB entry to be written. The EHB instruction is used to make sure all writes to coprocessor 0 have been completed before writing the TLB entry. Now, the TLB write index instruction is used to write the TLB entry. The address written to the TLB is advanced, so each will be different. Next is the branch instruction. Here the code compares the TLB index value that is in V1 with 0, and if they are not equal, the code branches back to the next TLB entry pair. The last instruction is in the branch delay slot and will always be executed. It uses the add instruction to increment the index value by a -1. Once the loop is complete, the code returns to start.s. The code walkthrough continues in Part 2.